This is part 2 of the lecture covering one-dimensional motion with constant acceleration. Towards the end of part 1 of the lecture, I derived for us the following 2 kinematics equations. These 2 kinematics equations are a complete description of this type of motion. They give us the position and the velocity of an object undergoing this type of motion at any time in the future, provided that we know 3 things about the object: its initial position x0, its initial velocity v0, and its constant acceleration a. Now you understand exactly what these equations are saying by using them, that is, by using them in examples. That's what I'm about to do here. Before I do, however, what I want to do formally for you is I want to lay out for you the methodology that you always use when solving a physics problem. To some extent, I've already been using this methodology throughout the year thus far, but let me go ahead here at this point and then write it out for you formally. So the first thing that you do when solving a physics problem is you draw a diagram. Simple as that. Okay, and then secondly, usually in basic examples, a number of quantities are given. Write them down. Write down the known quantities. Okay, third, you then write down the unknown quantities. Usually, at least in part, that's what's being asked for in the example. Fourth, you write the relevant equations. And then, as you'll discover with practice, these first 4 steps are most of the game, because then what remains is whatever mathematical manipulation that you have to go through to solve for whatever it is that you're looking for. Divide up the math, however, into 2 parts. The first thing you want to do is you want to make the math as easy on yourself as possible. So then, therefore, you plug in the quantities that are given as 0. You plug in your zeros. And then lastly, you then solve for whatever it is that you're looking for. So now let me go ahead and use this methodology specifically to the first of today's lecture examples. So go ahead and write down that example in your notes. Let me go ahead and read it to you. It's cast up here onto my screen. A rocket accelerates at a constant 9.8 meters per second squared after starting from rest. In part A, how much time in days is necessary for the rocket to reach a speed of 1/10 the speed of light? The speed of light is one of nature's fundamental constants. It's 3 times 10 to the 8th meters per second. That number will become very important later on in this year, but for now we're given the final velocity of the rocket as 1/10 of that value. And then in part B of the problem, it asks for the distance traveled by the rocket in terms of AU, astronomical units. So now let me go ahead and use this method to begin to solve this problem. The first thing to do is draw a simple diagram. So here's the rocket to begin. Here's the rocket to end. And then the next thing that we do is we write down the known quantities. Even though it doesn't explicitly say so in the problem, let's just immediately assume that the rocket begins at the origin. So then therefore the initial position x0 is equal to 0. It does say that the rocket begins at rest. So its initial velocity v0 is equal to 0, and then the rocket accelerates at 9.8 meters per second squared. When I said that earlier in the problem, you may have recognized that number and you may have said to yourself, that has something to do with gravity. That is correct. 9.8 meters per second squared is acceleration due to gravity. We'll get to that, however, later on in this chapter. For now, let's just go ahead and use that number in this problem. Now, right here is the acceleration vector A of the rocket to the right-hand side at 9.8 meters per second squared. At this point, just drawing the vector itself is perfectly fine. I don't have to draw a number line associated with it or anything like that. That's redundant. And then in part A, we're also given one last thing about the rocket, and that's its final velocity. So right here is the final velocity vector v of the rocket, and the magnitude of it is given to us as 3 times 10 to the 7th meters per second. 3 times 10 to the 7th is 1/10 of 3 times 10 to the 8th meters per second. And then we have our unknowns. We don't know the time over which this occurs, nor do we know the distance traveled by the rocket. The distance traveled by the rocket, however, is nothing more than the magnitude of the final position vector. So with respect to the origin, right here is the final position vector x. The magnitude of it is unknown. So now I've completed the first 3 steps of the method. The next thing to do is to write down the relevant equations. This is one-dimensional motion with constant acceleration, so then therefore we have the following equations. Here's the position as a function of time, and then here's the velocity as a function of time. And now we get to our mathematical manipulation. Once again, simplify the equations as much as possible by first of all plugging in the zeros. I'll do that first in the velocity equation. In the velocity equation, the initial velocity v0 is equal to 0. So then therefore the velocity equation simplifies to become the following, like so. And then if you look at the expression carefully, you'll notice that there's actually only one unknown that's present there, and that's the time t, which we can now solve for. So divide the a here to the other side, and then solve for t. Like so. And then at this point, after I've done my algebraic manipulation, it's at this point now that I finally plug in my numbers. Get into that habit. Do all of your algebraic manipulations first, get to the end of the process, and then plug in your numbers. So I now have 3 times 10 to the 7th meters per second divided by 9.8 meters per second squared. Before I solve for the number on my calculator, let's first of all look at the units. Let's perform what is called a little bit of dimensional analysis. So in terms of the units, notice that the meters cancels here and here, and one of the seconds cancels here and here. And then what we're left with is 1 over 1 over seconds, which is then therefore a time in terms of seconds, as we should obtain here when solving for the time t. Sometimes in a problem, perhaps it's a little bit more difficult than this. You'll go through a number of algebraic steps, and then you may not be sure whether or not your algebraic equation is in fact correct. What you can then do is a little bit of dimensional analysis. Check the units. The units in this case should be a time in seconds, and they are. And now I can go ahead and plug in my numbers to get my answer. So I'm going to use my calculator to do so. 3 times 10 to the 7th divided by 9.8. I'm going to round this off a little bit, and the number that I obtain is 3.06 times 10 to the 6th seconds. 3.06 times 10 to the 6th is 3.06 million seconds. Let's put that into perspective, however, by converting this time into days. There are 60 seconds in a minute. There are 60 minutes in an hour. There are 24 hours in a day. 60 times 60 times 24 gives you the number of seconds in a day. The number of seconds in a day is 86,400. You will probably memorize that number fairly quickly here in this class. This conversion factor will pop up periodically over the course of the year. So let's go ahead and convert this into days by doing the following. I'm going to multiply by 1 day per 86,400 seconds. So the seconds cancels here and here, and then I'll end up with a time in terms of days. So divide out by 86,400, and this comes out to be 35.4 days, just over a month. Like so. So to summarize the problem thus far, if I take this marker, for example, and release it from rest like so, such that it accelerates at 9.8 meters per second squared, after a time of 35.4 days, it will have a speed of 1/10 the speed of light. And now in part B of the problem, let's go ahead and calculate the distance traveled. I'm going to do some erasing here in order to do so. Okay, now in order to calculate the distance traveled, let's look at the position equation. In the position equation here, two things are 0. The rocket begins at rest, that's V0, like so, and it begins at the origin. So these two terms here are equal to 0, and the position equation then becomes the following. At this point, there's no algebraic manipulation to perform. At this point, I could just go ahead and plug in my numbers. When I plug in for the time, do I plug in the time as 35.4 days, or do I plug in the time in terms of seconds, the value that I've kept here? We do so in terms of seconds. What happens now? Let's see when I plug the numbers in. I'll go ahead and write out the numbers for us first. So I have 1/2 times 9.8 meters per second squared for the acceleration, and then times 3.06 times 10 to the 6th seconds quantity squared. Like so. Let me once again do here a little bit of dimensional analysis for us and see what happens in terms of the units. So I have here seconds squared canceling out with a seconds squared like so. And then what I'm left with here is a distance in terms of meters. So let's go ahead and get that distance in terms of meters, and at the end of the problem I'll go ahead and convert it into astronomical units. All right, so let me just go ahead now and multiply the numbers out. So I have here 1/2 times 9.8, and then times 3.06 times 10 to the 6th, and then I square that number. And then what I end up with, I'll round it off once again, is about 4.59 or so, times 10 to the 13th meters. That's 4.6 roughly, times 10 to the 13th meters, that's about 46 trillion meters. That's about 46 billion kilometers. That's quite a long way. So to put this into perspective for us, let's go ahead and convert this into astronomical units. The distance from the Earth to the Sun is the definition of 1 AU. That distance is about 150 million kilometers. That's 1.5 times 10 to the 11th meters. So now let me go ahead and do this conversion by doing the following. Multiply by 1 AU per 1.5 times 10 to the 11th meters. The meters cancels out like so, and now let me go ahead and get this number. So divide by 1.5 times 10 to the 11th meters per AU, and I end up then, I'll round it off once again a little bit, with a distance of about 306 AU. The average distance that Pluto is from the Sun is 40 AU. This distance here is nearly 8 times that distance. So for example, if I take this marker and drop it like so, and I let it constantly accelerate at 9.8 meters per second squared, not for just a moment here at my desk, but for 35.4 days, it will reach a speed of 1/10 the speed of light, and it will travel a distance that is nearly 8 times the distance that Pluto is from the Sun. I will do another example in just a few moments. Let me, however, go ahead and conclude this as part 2 of this lecture.